You already know about the double slit experiment, or you think you do. A particle is fired at a barrier with two slits. If nobody checks which slit it goes through, it produces an interference pattern on the detector behind the barrier, waves. If someone places a detector at the slits to watch which path the particle takes, the interference pattern vanishes. Particles. Observation collapses the wave function. You look, and reality changes. That is the version you were taught. It is on every popular science channel. It is in every physics textbook written for a general audience in the last 40 years. And it is not wrong exactly, but it is incomplete in a way that should genuinely disturb you. Because starting in 1982 and accelerating through a series of experiments that most people have never heard of, physicists discovered a second layer underneath that story. And the second layer does not care about you. It does not care about consciousness. It does not care whether anything is alive or aware or has any capacity for experience whatsoever. In 2012, a team at the Austrian Academy of Sciences in Vienna ran a version of this experiment where the choice to observe or not observe was made by a quantum random number generator, a machine. No human in the loop, no consciousness anywhere near the decision. And the results were identical. The pattern changed. The particle's history reorganized itself to be consistent with a choice made by a device that has no more awareness than a light switch. And the part that should keep you up tonight is not that reality responds to observation. It is that reality responds to something else entirely, something that is not a mind, something that physicists, as of right now, cannot define, cannot explain, and cannot agree on. The double slit experiment has a second layer, and the second layer is worse than the first. But to understand why it is worse, you need to see the first layer clearly, not the simplified version. Not the cartoon version with a ball going through two doors, the actual experiments, the actual people who found them, and what it cost them. And that story starts not with quantum mechanics, but with a beam of sunlight, a thin card, and a man whose discovery was so threatening to the scientific establishment of his time that they buried it for a decade. Thomas Young was born in 1773 in Milverton, Somerset, to a Quaker merchant family, and by any reasonable standard, he was one of the most gifted human beings who ever lived. He could read fluently by age 2. He had read the Bible twice in its entirety before his 5th birthday. By his teenage years, he had studied 13 languages, including Arabic, Persian, Turkish, and Ethiopian. He earned his medical degree from the University of Göttingen in 1796. He became a Fellow of the Royal Society at 21. He made foundational contributions to optics, elasticity, color vision, Egyptology, and linguistics. Cambridge students called him Phenomenon Young, and they meant it as both a compliment and a warning. In 1801, Young was appointed Professor of Natural Philosophy at the Royal Institution in London, where he delivered 91 lectures over 2 years. And it was during this period that he performed what readers of Physics World would vote in 2002 as the most beautiful experiment in physics. Here is what he actually did, and it matters that you know this, because the modern textbook version gets it wrong in a way that obscures the entire point. Young did not use two slits in a screen. He directed sunlight through a small hole using a steering mirror to produce a narrow beam, and then he split that beam by placing a thin card edgewise into it. The two portions of light diffracted around either side of the card, overlapped on the far wall, and produced alternating bright and dark bands, interference fringes. He then performed the critical test. He pushed a second card toward one side of the first, blocking one of the two beams. The fringes vanished on both sides. That was the proof. The pattern required both beams interacting. Light was a wave. Young presented the results in his 1803 Bakerian lecture to the Royal Society, published in Philosophical Transactions the following year. He described it as So simple and so demonstrative a proof of the general law of the interference of two portions of light that he expected it to settle the debate between the wave and particle theories once and for all. It did not settle anything. It nearly destroyed his career. Henry Peter Brougham, co-founder of the Edinburgh Review and a devoted follower of Newton's particle theory of light, launched a series of anonymous attacks in January 1803 that were vicious even by the standards of the era. His opening salvo declared that Young's paper contains nothing which deserves the name either of experiment or discovery, and that it was destitute of every species of merit. Brougham had personal reasons for the vendetta. Young, writing under a pseudonym, had previously criticized a young gentleman in Edinburgh for rediscovering known facts. That young gentleman was Brougham. But personal grudge aside, Brougham represented something larger. He represented an establishment that could not accept evidence contradicting the dominant theory. Newton said light was particles. Newton was sacred. Therefore, evidence of waves was not evidence. It was heresy. The attacks worked. Young's optical research sank into what historians describe as virtual oblivion between 1804 and 1816. He abandoned optics. He turned to Egyptology and medical practice. He resolved that all future non-medical publications would be anonymous. The wave theory of light would not be vindicated until Augustin Fresnel and François Arago revived it in France, more than a decade later. Young died in 1829 of ossification of the aorta. His monument in Westminster Abbey, describing him as a man alike eminent in almost every department of human learning. Think about that for a moment. A man performed an experiment that revealed something fundamental about the nature of reality. The establishment buried it, not because the experiment was wrong, not because the evidence was ambiguous, but because the implication was too uncomfortable to absorb. The evidence said that what everyone believed about light was incomplete, and rather than update the model, the establishment attacked the person who found the evidence. That pattern has repeated itself across the entire history of quantum mechanics, and it is repeating itself right now with the second layer of the double slit experiment. The evidence has been published, it has been replicated, it has been peer-reviewed and confirmed across multiple laboratories on multiple continents, and the mainstream popular understanding of what the double slit experiment means is still stuck on a version of the story that was incomplete by 1982. That should make you angry, not because scientists are hiding the truth. They are not. The papers are public, but because the actual implications of what those papers say are too uncomfortable for popular science communication to deliver with a straight face. So they give you the first layer, the neat, clean, slightly spooky version where consciousness is special and observation is mysterious, and reality responds to human awareness. And they leave the second layer in the journals where it belongs, where it is technically available to anyone, but where almost nobody will ever look. You are about to look, but first, you need to understand something about the experiment itself. Not the metaphor, not the analogy with balls going through doors that every YouTube explainer uses. The actual physical experiment, what it requires, what it produces, and why 160 years after Young's sunbeam, there was still a raging debate about what it means. Because the modern version of the double slit experiment, the one done with single particles instead of beams of light, revealed something so deeply strange that Richard Feynman, who understood quantum mechanics better than almost anyone who has ever lived, said in 1965 that it contains the only mystery of quantum physics, not one of the mysteries. Every other quantum weirdness, entanglement, superposition, tunneling, all of it traces back to what happens when a single particle encounters two open slits. And what happens is this. You fire particles, one at a time, one electron, one photon, one atom. You wait until it has been detected before you fire the next one. There is zero chance of two particles being in the apparatus simultaneously. Each particle arrives at the detector as a single indivisible dot, a point. Unambiguously a particle, but after you fire thousands of them, one at a time, the dots accumulate into a pattern. And the pattern is not a random scatter. It is not two clusters behind the two slits, which is what you would expect if each particle went through one slit or the other like a bullet through a doorway. The pattern is an interference pattern. Bright bands and dark bands, the exact pattern you would get if each particle were a wave passing through both slits simultaneously and interfering with itself on the other side. Each particle is indivisible. Each particle goes through one slit, but the pattern they collectively produce is only possible if each particle went through both slits. That is the contradiction. That is what Feynman called the only mystery. A single particle, fired alone, with no other particles anywhere near it, somehow knows about both slits. It somehow explores both paths simultaneously, and when it arrives at the detector, it lands in a position that is consistent with wave interference, as if it had been in two places at once. Now here is where the first layer of the story kicks in, the part you have heard before. If you place a detector at the slits to determine which slit the particle actually went through, the interference pattern vanishes. Gone. You get exactly what you would expect from particles behaving like bullets. Two clusters, no interference. The act of determining the path destroys the pattern. The standard explanation for this, the one that has been repeated in every popular science book and documentary for decades, is that the detector disturbs the particle. The act of measurement physically kicks the particle, randomizes its momentum via the Heisenberg uncertainty principle, and washes out the delicate interference. That explanation is intuitive. It makes mechanical sense. A detector is a physical thing that interacts with a physical particle, and interactions have consequences. And it is wrong. Not entirely wrong, the uncertainty principle is real, and detectors do interact with particles. But in 1982, a theoretical physicist named Marlon Scully and his colleague Kai Druhl published a paper in Physical Review A that proved you can set up an experiment where which path information is obtained without any mechanical disturbance, large enough to explain the loss of interference. The interference does not disappear because the particle was kicked. It disappears because the particle became entangled with the detector. Information about the path became available, encoded in the quantum state of another system. And that availability of information, not the physical disturbance, is what kills the wave pattern. That distinction might sound academic. It is not. It is the crack through which the entire second layer of this experiment emerges. Because if it is not physical disturbance that matters, but information, then a set of questions opens up that the physics establishment has spent 40 years trying and failing to answer. What counts as information? Information available to whom? Does it matter if anyone ever reads the information? Does it matter if the information is recorded by a conscious observer or by a machine? Does it matter if the choice to record the information is made before, during, or after the particle has already been detected? Those questions are not philosophical, they are experimental. People built machines to test them, and the answers are what this video is about. But the answers came slowly, and before we get to the second layer, you need to see the first layer properly, not the metaphor, the real thing. Because the real experiments are stranger than the popular version, and the people who performed them paid prices that the textbooks never mention. The double-slit experiment with actual particles, not light, was first performed by a doctoral student named Claus Johnson at the University of Tübingen in 1961. And when I say he performed it, I mean he spent years of his life fabricating the apparatus by hand, because the technology to do what he needed did not exist. The slits had to be cut into copper foil at a width of approximately 300 nanometers. For scale, a human hair is roughly 75,000 nanometers wide. Johnson was cutting slits 250 times narrower than a hair into metal, using electron beam irradiation on silver-coated glass plates, working alone through late nights in a university basement. His supervisor was Gottfried Mollenstedt, known in the field as the German Pope of electron microscopy. Mollenstedt had invented the electron biprism in 1955, and Johnson's project was to push it further, to do with electrons what Young had done with sunlight 160 years earlier. The night the interference fringes appeared on the detector, Johnson called his colleague W. Dietrich, another doctoral student who happened to be working late. Dietrich came to look and exclaimed in Swabian dialect, "Du sen se jo de Streif." There are the stripes indeed. Those stripes were proof that electrons, individual particles of matter with measurable mass and charge, behave as waves when passing through narrow slits. The results were published in Zeitschrift für Physik in 1961. An English translation did not appear until 13 years later, in the American Journal of Physics in 1974. That is not a typo. 13 years, the experiment that proved the most famous thought experiment in physics was physically real languished in a German-language journal for over a decade. The editorial note accompanying the English translation observed that for decades, two-slit electron interference has been presented as a thought experiment, and that few such recent presentations acknowledge that the two-slit electron interference experiment has now been done. Johnson himself received, in the editor's words, few professional rewards for the work. Think about what that means. The most important demonstration experiment in the history of quantum mechanics was performed in 1961. The physics community treated it as a footnote. Feynman, in his 1965 lectures, was still describing the double-slit experiment as a thought experiment. "You should not try to set up this experiment," Feynman told his Caltech students. "This experiment has never been done in just this way." It had been done 4 years earlier in Tübingen, but the truly brain-breaking version came later. Johnson used a beam of electrons, thousands of them at once. The interference pattern appeared in real time from a continuous stream. What physicists really wanted to know was whether a single electron, fired completely alone, would still produce interference. Because if a single electron makes an interference pattern, then the electron is not interfering with other electrons. It is interfering with itself. It is somehow going through both slits simultaneously as a wave, and then arriving at the detector as a particle. The definitive answer came from Akira Tonomura and his colleagues at the Hitachi Advanced Research Laboratory in Japan, published in the American Journal of Physics in 1989. They used a field emission electron gun with extraordinary coherence, firing electrons through an electron biprism that served as the double-slit equivalent. The critical detail is that the electron intensity was kept below 1,000 electrons per second, and the apparatus was designed so that only one electron existed inside it at any given moment. There was zero chance of two electrons interacting, zero chance of one electron's wave function overlapping with another's. The images from Tonomura's experiment are among the most haunting in all of science. He published 4 stages of the build-up. After about 100 electrons, you see what looks like random noise, scattered dots with no discernible pattern. After about 3,000 electrons, faint hints of structure begin to emerge from the chaos, like a face forming in static. After about 20,000 electrons, the interference bands are clearly visible. And after about 70,000 electrons, the pattern is fully formed, unmistakable, exactly matching the prediction for wave interference through 2 slits. Each individual electron landed as a single dot, a particle hitting one specific point. Nothing wave-like about any individual detection. But the accumulation of 70,000 individual separate isolated particles produced a wave interference pattern. Each electron, fired alone, somehow contained information about both slits. Each electron, with no other electron anywhere near it, explored both paths simultaneously and arrived at a position consistent with the interference of waves. And here is where it gets worse. Because when Tonemura's team placed a detector to determine which slit each electron went through, the interference pattern vanished. It just disappeared. The electrons started behaving like bullets. 2 clusters behind the 2 slits. No interference, no wave behavior. The simple act of making the path information available collapsed the pattern into something ordinary. That result, confirmed hundreds of times across dozens of laboratories in the decades since, is the first layer of the double slit experiment. Particles behave as waves when nobody checks which path they take, and as particles when somebody does. Observation, whatever observation means, changes the outcome. That is the version you know. But here is the question that was already burning by the mid-1970s, the question the popular accounts of this experiment almost never ask. Why does observation change the outcome? What is it about a measurement that destroys interference? The standard answer, the one Bohr and Heisenberg established, and the one that became the default for most of the 20th century, is the uncertainty principle. The detector physically interacts with the electron. That interaction transfers momentum. The momentum transfer randomizes the electron's trajectory enough to wash out the delicate interference fringes. It is a mechanical explanation. The detector bumps the particle. The bump destroys the pattern. Simple. And in 1982, Scully and Druhl blew that explanation apart. Their paper, published in Physical Review A, Volume 25, showed theoretically that you can design an experiment where which path information is recorded without any momentum transfer large enough to explain the loss of interference. The information gets encoded not through a physical kick, but through quantum entanglement. The particle becomes correlated with another quantum system in a way that stores the path information, and the interference still vanishes, not because of a bump, because of information. This was confirmed experimentally in 1998 by Durr, Non and Remb at the Max Planck Institute, using rubidium atoms in an atom interferometer. They demonstrated, and I am quoting from their paper in Nature, that the back action of path detection on the atom's momentum is too small to explain the disappearance of the interference pattern. The interference vanished, not because of mechanical disturbance, but because of correlations, entanglement. The which path information existed, encoded in another system, and that was enough. Whether anyone read that information was irrelevant to the disappearance of the fringes. In 1996, the physicist Berthold Georg Englert formalized this into a precise mathematical relationship, published in Physical Review Letters. d squared plus v squared is less than or equal to 1. D is the path distinguishability, how much information is available about which slit the particle went through, measured on a scale from 0 to 1. V is the fringe visibility, how clear the interference pattern is, also 0 to 1. As one goes up, the other must come down, not because of any physical mechanism, because of information. If the information about the path is fully available, D equals 1 and V must be 0. No interference. If no path information exists, D equals 0 and V can reach 1. Full interference. The trade-off is not mechanical, it is informational. And that changes everything, because once you know that information is the variable, not physical disturbance, a door opens that leads somewhere physicists have been trying to avoid for 40 years. If it is information that kills interference, what happens if you create the information and then destroy it? What happens if you make the path knowable and then make it unknowable again? Does the interference come back? The answer is yes, and the experiment that proved it is one of the most misunderstood results in the history of physics. To get there, though, we need to take a detour through one of the strangest minds in the history of physics, because the experiment that cracked open the second layer of the double slit was not proposed by a rebel or an outsider. It was proposed by a man at the absolute center of the physics establishment, a man who had worked personally with Niels Bohr, who had named black holes and wormholes, who had helped build the atomic bomb, and who, at the age of 67, asked a question so unsettling that the physics community spent 2 decades pretending it was merely philosophical before anyone had the nerve to test it in a laboratory. John Archibald Wheeler was born on July 9, 1911, in Jacksonville, Florida. His parents were both librarians. He entered Johns Hopkins University at 16, earned his PhD at 21, and secured a National Research Council fellowship to study in Copenhagen under Niels Bohr, the architect of quantum mechanics, and the man whose interpretation of the theory would dominate physics for the rest of the century. Wheeler's fellowship application contained a single sentence that tells you everything about the kind of physicist he was. "I want to go to work with Niels Bohr because he sees further than any man alive." He arrived in Copenhagen in 1934 and spent a year absorbing Bohr's philosophy of complementarity, the idea that certain descriptions of reality are mutually exclusive but jointly necessary. A particle is a wave. A wave is a particle. Neither description is complete alone. Both are required. The act of measurement determines which description applies. Wheeler internalized this deeply, but he would spend the rest of his life pushing it further than Bohr ever intended. In January 1939, Bohr arrived at Princeton University carrying news that would change the world. German chemists Otto Hahn and Fritz Strassmann had split the uranium atom. Nuclear fission was real. Bohr and Wheeler immediately began collaborating on the theoretical framework for fission, and on September 1, 1939, the day Germany invaded Poland, they published The Mechanism of Nuclear Fission in Physical Review. Wheeler was 28 years old. Their paper identified uranium-235 as the highly fissile isotope and laid the groundwork for everything that followed. Wheeler threw himself into weapons work during the war. He moved to the Hanford site in Washington state, where the B reactor was producing plutonium for the bomb. When the reactor mysteriously shut itself down shortly after achieving criticality, Wheeler was the one who identified the cause. Xenon-135, a fission product with an enormous neutron absorption cross-section, was poisoning the reactor. His solution saved the plutonium production program and, by extension, the Manhattan Project's timeline. But there is a part of this story that the physics textbooks leave out. Wheeler had a brother. His name was Joe. Joe Wheeler was fighting in the Italian campaign while his older brother was building weapons at Hanford. Joe knew, in the vague way that family members of classified project workers sometimes know, what his brother was doing. He sent Wheeler a postcard. It contained 2 words: "Hurry up." Joe Wheeler was killed in Italy in October 1944. He left behind a widow and a baby daughter. The bomb was not ready. It would not be used until August 1945, 10 months after Joe's death. Wheeler spent the rest of his life carrying that arithmetic. He wrote later, "Here we were, so close to creating a nuclear weapon to end the war. I could not stop thinking then, and have not stopped thinking since, that the war could have been over in October 1944. In December 1968, President Johnson presented Wheeler with the Enrico Fermi Award, one of the highest honors in American science. Wheeler's response was 3 words: "I felt forgiven." I am telling you this not because it is interesting background, but because it connects directly to what Wheeler did next. Because the man who spent decades haunted by the question of whether the past could have been different, whether a different timeline was possible, whether the sequence of events that led to his brother's death could have been altered by a faster decision, became the man who asked whether the past is actually fixed at all, whether a choice made now can reach backward and determine what happened then. Wheeler's first graduate student at Princeton was Richard Feynman, who arrived in the fall of 1939, the same week the fission paper was published. In the spring of 1940, Wheeler called Feynman on the phone with an idea so wild that Feynman remembered the conversation for the rest of his life. Feynman, Wheeler said, "I know why all electrons have the same charge and the same mass." Feynman asked why, because they are all the same electron. Wheeler proposed that every electron in the universe was a single entity zigzagging through time, appearing as an electron when moving forward and as a positron when moving backward. The entire visible universe was one particle's infinitely tangled world line. Feynman did not take the full idea seriously, but he later acknowledged, "I did not take the idea that all the electrons were the same, one from him as seriously as I took the observation that positrons could simply be represented as electrons going from the future to the past in a back section of their world lines. That I stole." That stolen insight became central to Feynman diagrams, to quantum electrodynamics, and to Feynman's 1965 Nobel Prize. Wheeler had a habit of throwing out ideas so radical that even the geniuses around him could only absorb half of them. The other half would turn out to be right decades later. Wheeler also supervised Hugh Everett III, whose 1957 doctoral thesis at Princeton proposed the most radical interpretation of quantum mechanics ever conceived. Everett suggested that the wave function never collapses. Every quantum measurement causes the universe to split into branches, one for each possible outcome. All outcomes are real. All branches exist. The cat is alive in one universe and dead in another, and both universes are equally physical. Wheeler championed Everett's thesis. He personally traveled to Copenhagen to present it to Bohr. Bohr rejected it completely. Wheeler then made Everett cut the thesis roughly in half, removing the most provocative philosophical implications. Everett, already feeling marginalized, took a job at the Pentagon doing operations research. He never published another physics paper. He became increasingly reclusive, drank heavily, and died of a heart attack in 1982 at the age of 51, legally drunk at the time of death. He had asked that his ashes be thrown in the trash. His wife complied. His daughter Elizabeth struggled with mental illness for years afterward. She died by suicide in 1996. Her suicide note expressed the hope that she would end up in the correct parallel universe to meet up with Daddy. Whatever you think about the many worlds interpretation, that sentence should be hard to read. Wheeler himself eventually abandoned Everett's interpretation. In 1980, he told a colleague that it carried too great a load of metaphysical baggage. The man who had championed the idea walked away from it. The man who had proposed it drank himself to death. And the interpretation itself, dismissed for decades as science fiction, is now considered by many physicists to be the most mathematically consistent way to read the equations of quantum mechanics. Sean Carroll has called it not an interpretation, but a discovery. David Deutsch has said dismissing it is like dismissing dinosaurs as an interpretation of fossil records. The cosmic irony is suffocating. The idea that destroyed its creator's life may turn out to be the correct description of reality. And the mentor who abandoned both the idea and its creator may have been the man best positioned to bring them both in from the cold. But Wheeler did not walk away from the question. He walked toward a different version of it. And in 1978, at a symposium honoring Feynman, Wheeler presented a thought experiment that was, in its way, even more disturbing than many worlds, because many worlds at least preserved the idea that the past is fixed. In many worlds, the universe branches at the moment of measurement, but each branch's past is determined. Wheeler's delayed choice experiment suggested something worse. It suggested that the past is not fixed at all, that a decision made now can reach backward and determine what a particle did before the decision was made. Here is the setup. You fire a single photon at a half-silvered mirror, a beam splitter. The photon has a 50% chance of passing through and a 50% chance of being reflected. If it passes through, it takes path A. If it is reflected, it takes path B. Mirrors redirect both paths to a crossing point. At the crossing point, you have a choice. You can place detectors along each path. If you do, the photon is detected on one path or the other. It went through the beam splitter and took a definite route, particle behavior. Or you can place a second beam splitter at the crossing point, recombining the paths. If you do, the two paths interfere. The photon behaves as if it traveled both paths simultaneously. Wave behavior. Wheeler's question was simple. What if you make that choice after the photon has already passed the first beam splitter? What if the photon has already decided its route, already committed to path A or path B, or both, and then you choose whether to insert the second beam splitter or not? Quantum mechanics predicts that it does not matter when you choose. If you insert the second beam splitter, you get interference, wave behavior. If you do not, you get which path detection, particle behavior. Regardless of the fact that the photon entered the apparatus before your choice was made, the photon's behavior in the past conforms to a decision made in its future. Wheeler did not think this was about time travel. He did not think a signal was being sent backward. He thought the lesson was more fundamental than that. He wrote, "It is wrong to speak of the route of the photon in the experiment of the beam splitter. It is wrong to attribute a tangibility to the photon in all its travel from the point of entry to its last instant of flight. The photon does not have a past until a measurement defines one. The past is not a fact waiting to be discovered. It is a story that is written by the act of measurement itself." And then Wheeler took the idea cosmic. He pointed to quasar 0957 plus 561, discovered by Walsh, Carswell and Wayman in 1979. A single quasar whose light is split by the gravitational field of a foreground galaxy into two images separated by 6 arcseconds. The light takes two different paths around the galaxy, and those paths differ in length by billions of light years. The photons have been traveling for roughly 9 billion years along two separate routes. An astronomer on Earth, by choosing to measure which path or to recombine the beams for interference, could retroactively determine what the photon did 9 billion years ago, before the Earth existed, before the solar system formed, before there was any life anywhere in the universe to observe anything. Wheeler wrote, "Thus the observing device in the here and now, according to its last-minute setting, one way or the other, has an irretrievable consequence for what one has the right to say about a photon that was given out long before there was any life in the universe." And his most famous line from this period, the one that gets quoted in every documentary about quantum mechanics, but whose full implications are almost never unpacked, was this: "We are participators in bringing into being not only the near and here, but the far away and long ago." That is an extraordinary sentence. Read it again. Wheeler is not saying that we discover the past. He is saying we participate in creating it. The act of measurement does not reveal a pre-existing fact about the photon's history. It brings that history into being. But here is what almost nobody tells you. Wheeler did not think this was about consciousness. He did not think human awareness was the special ingredient. Late in his career, Wheeler developed a framework he called it from bit. Every particle, every field of force, every space-time coordinate, he argued, derives its existence entirely from what he called apparatus-elicited answers to yes or no questions, binary choices, bits. Not bits in a computer, bits in reality. The universe, at its deepest level, is not made of matter or energy. It is made of information, and information does not require a mind to exist. That idea, proposed in 1989, has been sitting there for over 35 years. It should have transformed how the public understands quantum mechanics. It did not. Because the consciousness story is sexier. The consciousness story makes humans special. The consciousness story puts us at the center of the universe in a way that feels spiritual, mystical. Wheeler's idea takes us out of the center. It says the universe does not need us. It says information is the variable, not awareness. And that is a much harder sell on a YouTube thumbnail. But the experiments kept confirming Wheeler's prediction, not the consciousness story. First in the laboratory, then at cosmic scales, and then starting in 2012 with machines that removed human beings from the equation entirely. The delayed choice experiment was first realized in the laboratory by Carol Alley, Oleg Yakubovitz, and William Wicks at the University of Maryland in the mid-1980s, with results published in the Proceedings of the Second International Symposium on Foundations of Quantum Mechanics in Tokyo in 1987. Independently, Helmuth, Walther, Zajonc, and Schleich at the Max Planck Institute for Quantum Optics published 2 delayed choice experiments in Physical Review A in 1987, confirming no observable difference between normal and delayed choice modes of operation, in agreement with the predictions of quantum mechanics. But the definitive version came in 2007. Vincent Jacques and a team including Alain Aspect, one of the most important experimental physicists alive, published their results in Science. They used true single photons from individual nitrogen vacancy color centers in diamond nanocrystals, pumped by a 532 nanometer laser. The Mach-Zehnder interferometer they built had 48 meters between input and output beam splitters, ensuring that the photon had long since passed the first beam splitter before the delayed choice was made. And the choice was not made by a human. It was made by a quantum random number generator sampling amplified shot noise from white light. The results were unambiguous. When the random number generator chose the wave configuration, the photon showed 94% interference visibility. When it chose the particle configuration, path determination had an error probability below 1%. There was no difference between the delayed choice and a normal preset choice. Wheeler's prediction, made as a thought experiment in 1978, was confirmed with single photons and a machine making the decision. The photon's past was determined by a choice made after the photon had already entered the apparatus, and the choice was made by a machine. That was 2007, and it should have been the end of the consciousness story right there. A random number generator determined whether a photon behaved as a wave or a particle, and the photon complied. No consciousness required. But the story did not end there, because in the years that followed, a series of experiments pushed the implications even further, and they involved not just the delayed choice, but the quantum eraser, the most misunderstood experiment in the history of physics, and the one that contains the second layer that this video is about. The quantum eraser experiment has been explained on YouTube more times than anyone can count, and almost every explanation gets it wrong. Not slightly wrong. Wrong in a way that makes the result seem less disturbing than it actually is, because the wrong version replaces the real implication with a more comfortable one. The wrong version says the experiment proves that consciousness can reach backward through time and change the past. That sounds spooky. That sounds mystical. That makes for a great thumbnail. But it is not what the experiment shows. What the experiment actually shows is worse, because it removes consciousness from the equation entirely and replaces it with something we cannot name. Let me walk you through the actual experiment, not the simplified version, the real one. Because the details matter, and the details are where the second layer lives. The landmark version was performed by Yoon-Ho Kim, R.U., SP, Kulik, Y.H. Shish, and Marlin Scully, the same Scully who had proposed the quantum eraser concept 16 years earlier. It was published in Physical Review Letters on January 3, 2000, and conducted at the University of Maryland, Baltimore County. Here is what they built. A 351.1 nanometer argon ion laser fires a pump beam through a double slit and into a special crystal called a BBO crystal. BBO stands for beta barium borate. This crystal does something remarkable. Through a process called spontaneous parametric down conversion, it takes a single high-energy photon and converts it into two lower-energy photons. These two daughter photons are called the signal photon and the idler photon. They are entangled. Born together from the same parent photon, their quantum states are correlated in a way that classical physics cannot explain. Each pair has a combined wavelength of 702.2 nanometers, which is near infrared. Here is the critical part of the geometry. The double slit has two regions where down conversion can happen. Call them region A and region B, corresponding to the two slits. Each region is approximately 0.3 millimeters wide, and they are separated by approximately 0.7 millimeters. When a pump photon passes through region A, it creates a signal idler pair from slit A. When it passes through region B, it creates a signal idler pair from slit B. The signal photons and idler photons are then separated by a prism and sent in different directions. The signal photon is directed through a lens toward a detector called D0, which can be physically scanned along the x-axis by a step motor. D0 records where the signal photon arrives. This is the screen where the interference pattern would appear, if there is one. The idler photon enters a completely separate optical system. A prism deflects the idler along different paths depending on whether it came from slit A or slit B. These paths encounter two 50-50 beam splitters labeled BS sub A and BS sub B, one for each path. The beam splitters each give the idler photon a 50% chance of being transmitted or reflected. And this is where the choice happens. Not a human choice, a quantum random event at a beam splitter. If the idler from slit A is transmitted through BS sub A, it goes to detector D3. D3 can only receive idlers from slit A. It provides which path information. You know the signal photon's partner came from slit A, which tells you the signal photon itself came from slit A. If the idler from slit B is transmitted through BS sub B, it goes to detector D4. D4 can only receive idlers from slit B. Same logic. Which path information is preserved? But if the idler from either slit is reflected by its beam splitter, instead of transmitted, it continues to a final beam splitter called BS, where idlers from path A and path B are recombined. At this final beam splitter, the two paths become indistinguishable. You can no longer tell whether the idler came from slit A or slit B. The which path information has been erased. These recombined idlers go to detectors D1 and D2, and here is the part that matters most. The optical path length from the BBO crystal to D0 is 2.5 meters shorter than the path from the BBO crystal to the idler detectors. This means the signal photon arrives at D0 about 8 nanoseconds before the idler photon reaches its detector. The signal photon has already been detected, its position already recorded, its dot already on the screen, before the idler photon encounters the beam splitter that determines whether which path information is preserved or erased. Now for the results. And this is where you need to pay close attention, because what the experiment found is not what most people think it found. If you look at D0 on its own, at all the signal photon detections without sorting them by anything, you see nothing. No interference pattern, no fringes, just a smooth, featureless blob, a single broad hump. This is important. If you were standing in the laboratory watching the signal photon detector in real time, you would see absolutely no evidence of interference, no matter what happens to the idler photons. This never changes, The total unsorted pattern at D0 is always a blob. But when the researchers sorted the D0 detections by which idler detector fired, using a process called coincidence counting, the blob decomposed into 4 distinct subpatterns. R01, the signal photon detections coincident with idler detections at D1, where which path information had been erased, showed a clear interference pattern. Young's fringes, bright bands and dark bands. R02, the coincidences with D2, also where which path information was erased, showed an interference pattern too, but this pattern was phase shifted by pi relative to R01. The peaks of R01 aligned with the troughs of R02, and vice versa. RN03, the coincidences with D3, where which path information was preserved, showed no interference, just a smooth hump. R04, the coincidences with D4, also preserving which path information, showed no interference either. Another smooth hump. And here is the mathematical punchline. R01 and R02 are complementary interference patterns. When you add them together, the peaks and troughs cancel out perfectly, producing a smooth hump. Add that to R03 and R04, which are also smooth humps. The sum of all 4 subpatterns equals the total blob at D0. The interference was always there hidden inside the data, but it was exactly cancelled out by its own complement. You can only see it by sorting, and you can only sort by using the idler information, which arrives after the signal photon has already been recorded. This is the result that launched 1,000 wrong YouTube videos. Because it looks, at first glance, like the future is determining the past. The idler photon's detection happens after the signal photon's detection. The idler's fate determines whether the signal photon subset shows interference or no interference. Therefore, the logic goes, the future changed the past. The signal photon retroactively went through both slits, or one slit depending on what happened to its partner, 8 nanoseconds later. But that is not what is happening. And understanding why it is not what is happening is the key to understanding the second layer. The signal photon and the idler photon are entangled from the moment they are created at the BBO crystal. Entanglement means their quantum states are correlated. And here is what most popular accounts leave out. Entanglement itself destroys interference. The signal photon, by virtue of being entangled with the idler, is not in a pure quantum state. It is in what physicists call a mixed state. Its reduced density matrix has no off-diagonal coherence terms. There are no interference fringes to see, not because someone looked, not because a conscious mind observed something, because the signal photon is part of an entangled pair, and entangled particles do not show single particle interference. Full stop. Sean Carroll put it bluntly. Entanglement of any sort kills interference. So the interference was already dead the moment the photon pair was born. What the eraser detectors do is not reach backward in time to resurrect it. What they do is post-select. They sort the already recorded D0 data into subsets. In the subsets where the idler's which path information was erased, the mathematical structure of the two-photon wave function allows an interference pattern to appear when you look at only that subset. In the subsets where which path information was preserved, it does not. But the signal photons in both subsets hit D0 at the same time, in the same place, with the same total distribution. You cannot tell from looking at D0 in real time which subset any individual photon belongs to. You need the idler data, and the idler data travels to you at the speed of light. You cannot access it faster. You cannot use this experiment to send a signal backward in time. Ruth Kastner, in a 2019 analysis, wrote that the experiment neither erases nor delays. Johannes Fankhauser at the University of Innsbruck noted that it resembles a Bell-type scenario in which the paradox's resolution is rather trivial. And Sabine, Hossenfelder's analysis correctly emphasized that no one looking at D0 in real time can ever distinguish any pattern from the blob. The sorted subpatterns are visible only after the classical information about idler detections has been communicated to the person analyzing the data. Now here is where most explanations stop. They debunk the retrocausality claim, they explain entanglement and post-selection, and they move on. But this is exactly the point where the second layer begins. Because debunking the consciousness reaches backward through time story is not the end of the mystery. It is the beginning of a deeper one. The comfortable misinterpretation was that consciousness matters, that human observation is special, that the universe responds to awareness, to intention, to a mind that chooses to look. That misinterpretation, wrong as it is, at least preserves the idea that we are important, that human beings have a special relationship with reality, that the universe, in some deep way, cares about us. The actual result is worse. The actual result is that the universe does not care about us at all, not in a cold, indifferent Carl Sagan, pale blue dot kind of way, in a more specific, experimentally verified way. The interference pattern does not vanish because a human looked. It vanishes because information became available, not available to a mind, available in principle, encoded in the quantum state of another system. Whether that system is a conscious human being, a photon detector, a random number generator, or a stray molecule of air makes no difference whatsoever. The only thing that matters is whether which path information is, in principle, accessible somewhere in the physical world. If it is, the interference is gone. If it is not, the interference remains. You are not the observer the universe is responding to. You never were. And in 2012, a team in Vienna set out to prove exactly that. Not as a philosophical argument, as an experiment, with machines, random number generators, and photons traveling 144 kilometers between islands in the Atlantic. What they found is the second layer. And the second layer says something about the nature of reality that mainstream physics communication has been unwilling to say out loud for over a decade. That the universe does not just fail to require consciousness. It actively does not distinguish between a conscious choice and a mechanical one, between a deliberate observation and an accidental interaction, between a physicist making a measurement and a photon bouncing off a dust grain. The variable is not who observes. The variable is not even whether anyone observes. The variable is whether the information exists. And exists does not mean exists in someone's mind. It means exists anywhere in the physical world, in any form, accessible or not, read or unread, known or unknown. The experiments that proved this were run between 2012 and 2018. They removed every possible role for consciousness, one experiment at a time, like pulling legs off a table to see when it falls. It never fell. The quantum effects remained with every leg removed. The table, it turned out, was not standing on consciousness at all. It was standing on something else. The first experiment came from Anton Zeilinger's group at the Institute for Quantum Optics and Quantum Information in Vienna. Zeilinger, who would win the 2022 Nobel Prize in Physics, alongside Alain Aspect and John Clauser, had spent decades pushing quantum teleportation. He had sent entangled photons between the Canary Islands across a 144-kilometer gap. He had bounced entangled photons off satellites, and in 2012, he and his team published a paper in Nature Physics that in a just world would have made the front page of every newspaper on Earth. The paper was authored by Xiaosong Ma, Stefan Zotter, Johannes Koffler, Rupert Ursin, Thomas Genowain, Kaslav Bruckner, and Zeilinger. It was titled experimental delayed choice entanglement swapping. And what it demonstrated was this. Two separate sources produced two pairs of polarization entangled photons. Call the photons 1 and 2 from the first source and 3 and 4 from the second source. Alice measured photon 1. Bob measured photon 4. Both measurements happened immediately, approximately 35 nanoseconds after the photons were produced, through 7-meter fiber paths. Alice and Bob each chose freely among 3 mutually unbiased polarization bases. Their results were recorded permanently, irreversibly. Done. Photons 2 and 3, meanwhile, traveled through much longer fibers, 104 meters of optical fiber. They arrived at a third location operated by a character the paper calls Victor, approximately 520 nanoseconds after the photons were produced. That is nearly half a microsecond after Alice and Bob had already measured and recorded their results. Victor's apparatus could do one of two things, and the choice was made by a quantum random number generator. Not a human, not a consciousness. A machine that samples quantum noise and outputs random bits. If the machine chose option 1, Victor's apparatus performed a Bell state measurement on photons 2 and 3, projecting them onto entangled Bell states. This operation, through the mathematics of entanglement swapping, retroactively entangled photons 1 and 4, photons that had never interacted, photons that had been produced by completely separate sources, photons that had already been measured by Alice and Bob before Victor's machine made its choice. Those photons, after Victor's measurement, showed quantum correlations. They violated Bell inequalities. They were entangled. If the machine chose option 2, Victor's apparatus performed a separable state measurement instead. In this case, photons 1 and 4 showed only classical correlations. No entanglement, no Bell violation. Just ordinary explainable correlations consistent with classical physics. Let me state that again, because the implication needs to land. Alice and Bob measured their photons and recorded the results before Victor's machine made any choice. The data was written, the ink was dry, and then, half a microsecond later, a quantum random number generator flipped a bit, and the nature of the correlations in the already recorded data changed. When the researchers went back and sorted Alice and Bob's data by what Victor's machine had chosen, the sorted subsets showed either quantum entanglement or classical correlation, depending on a choice made after the data was collected. The paper's authors wrote, if one viewed the quantum state as a real physical object, one could get the paradoxical situation that future actions seem to have an influence on past and already irrevocably recorded events. No human consciousness anywhere in the decision chain. A machine chose. The past reorganized. The following year, the same group published an even more extreme version. Ma, Koffler, and Zeilinger, along with several colleagues, published Quantum Erasure with Causally Disconnected Choice in the Proceedings of the National Academy of Sciences in 2013. This time, the choice of whether to erase which path information was made under Einstein locality conditions, space-like separation. The choice event and the photon's passage through the interferometer were separated by enough distance that not even light could connect them. No signal, no influence, no causal connection of any kind could exist between the choice and the measurement in any reference frame under the rules of special relativity. They ran the experiment in 2 configurations, a 55-meter fiber link in a Vienna laboratory and a 144-kilometer free space link between La Palma and Tenerife in the Canary Islands. A quantum random number generator made every decision. The results, once again, matched quantum mechanical predictions exactly. When the machine erased which path information, interference appeared in the coincidence counted subsets. When the machine preserved which path information, no interference appeared. under conditions where not even the laws of physics permitted a causal connection between the choice and the experiment. The paper concluded, "No naive realistic picture is compatible with our results because whether a quantum could be seen as showing particle or wave-like behavior would depend on a causally disconnected choice. A causally disconnected choice, made by a machine, with no consciousness, no intention, no understanding. And reality obeyed." But the most direct test of whether human consciousness produces any different result from machine randomness came in 2018, and it involved not a small team in a single laboratory, but over 100,000 people on 5 continents playing a video game. The Big Bell Test Collaboration, published in Nature in 2018, organized a global event on November 30th, 2016. 100,000 human participants worldwide generated 97,347,490 random bits by playing an online video game designed to produce unpredictable sequences. These bits were streamed in real time to 13 experiments running in 12 laboratories on 5 continents, replacing physical random number generators in Bell test experiments. The results confirmed violations of local realism across all 13 experiments. But the finding that matters for our purposes came from the Munich experiment run by the Max Planck Institute for Quantum Optics and Ludwig Maximilian University. That experiment explicitly compared human-decided measurement settings against quantum random number generator decided settings, and the two produced identical Bell inequality violations. Not similar, identical. Statistically indistinguishable. 100,000 human minds making choices. Machines making choices, the universe responding the same way to both. There is no experiment in the history of quantum mechanics that has ever found consciousness to matter. Not one. Every experiment ever designed to test whether human awareness plays a special role has found that it does not. The universe does not distinguish between you and a random number generator, between a decision made by a Nobel laureate and a decision made by electronic noise, between a thought and a coin flip. That should be the story that every popular science channel tells. That should be the version of the double slit experiment that is taught in every physics class. Not the first layer, not the spooky consciousness version, not the universe responds to observation, framing that implies human minds are doing something special. The actual result. The second layer, the one where consciousness is removed from the equation and nothing changes. But that story is almost never told, and you need to ask yourself why. Part of the answer is structural. The consciousness version is a better story. It makes humans the protagonist. It makes quantum mechanics feel like it has something to do with your everyday experience, your awareness, your inner life. It plays into existing cultural narratives about the power of the mind, the mystery of consciousness, the special place of humanity in the cosmos. Those narratives sell books. They sell documentaries. They sell courses on manifesting your reality through quantum intention. The consciousness version of the double slit experiment has spawned an entire industry of pseudoscience built on a fundamental misreading of the experimental data. But another part of the answer is more uncomfortable. The actual result is harder to process. If the universe is not responding to consciousness, what is it responding to? You can say information, and the word feels like it explains something. But when you push on it, the explanation dissolves. What is information? Is it a physical thing? A property of matter? A mathematical abstraction? Is it fundamental, meaning the universe is built out of information at the lowest level? Or is it derived, meaning information is just a label we attach to patterns in matter and energy? Physicists do not agree. They do not even agree on whether the question makes sense. And yet the experiments keep pointing in the same direction. Every test that has ever been run says the same thing. The variable that determines whether quantum interference appears or disappears is not consciousness, not physical disturbance, not the type of detector, not whether the measurement is made by a human or a machine. The variable is whether which path information is, in principle, available anywhere in the physical universe. If the information exists, interference dies. If the information is erased, interference can return. If the information is created and then destroyed before it can be accessed, the interference comes back as though it were never gone. The universe is not responding to being watched, it is responding to the existence of a record. And a record does not need anyone to read it. In the remaining sections, we need to confront what this actually means. We need to look at what observation really is according to modern physics, why 6 different interpretations of quantum mechanics disagree about almost everything except the irrelevance of consciousness, and what Wheeler meant when he said the universe derives its existence from bits. Because the second layer does not end with removing consciousness from the equation. That was just the door opening. What is on the other side of that door is a picture of reality where information is more fundamental than matter, where the past is not fixed until the present defines it, and where the thing that makes reality real is not substance or energy or mind, but something that physicists have spent 40 years struggling to name. Something that John Archibald Wheeler, the man who worked with Bohr and mentored Feynman and named black holes and carried the weight of his brother's death for 60 years, spent the last decades of his life trying to articulate. He called it from bit. And what he meant by that might be the most important idea in the history of physics that you have never heard of. But before we get to Wheeler's answer, there is one more experiment you need to see, because the experiments we have discussed so far removed consciousness from the decision to observe. They showed that a machine can make the choice and the results are the same. But they did not directly test the most radical claim that comes out of quantum mechanics. They did not test whether reality itself is observer-dependent, whether 2 different observers looking at the same experiment can get results that are fundamentally irreconcilable. Not just different perspectives on the same event, but genuinely contradictory facts about what happened. In 2019, a team at Heriot-Watt University in Edinburgh built a machine that tested exactly that, and the result should have shaken physics to its core. The experiment was designed by Massimiliano Proietti and 6 colleagues, published in Science Advances in September 2019. It was based on a thought experiment first proposed by the physicist Eugene Wigner in 1961, which had been extended into a testable framework by Čáslav Bruckner at the University of Vienna. The thought experiment goes like this. Wigner has a friend. The friend is inside a closed laboratory, performing a quantum measurement. Say the friend measures the polarization of a photon. She gets a definite result, horizontal or vertical. To the friend, the measurement is over. She knows the answer. The photon has a definite polarization. That is a fact. But Wigner is outside the laboratory. From Wigner's perspective, the laboratory is a quantum system that includes the friend, the photon, and the measuring apparatus. And according to quantum mechanics, until Wigner opens the door and checks, the entire laboratory is in a superposition of friend measured horizontal and friend measured vertical. To Wigner, the friend has not gotten a definite result. The measurement is not over. There is no fact yet. This is not a disagreement about what they know. This is a disagreement about what exists. The friend says the photon has a definite polarization. Wigner says it does not. They cannot both be right, and yet quantum mechanics applied consistently says they are both applying the rules correctly. For decades, this was treated as a philosophical curiosity. Nobody thought it was testable because you cannot put a human being in a quantum superposition. But Proietti's team realized you do not need a human, you need a photon acting as the friend, making a measurement on another photon. And then you need an outside observer making a measurement on the entire system. They built a 6-photon experiment. 2 photonic friends perform measurements inside their laboratories. 2 Wigners measure from outside. The experiment tests a Bell-type inequality that assumes 3 things. First, that quantum mechanics applies universally to systems of any size. Second, that different observers can reason consistently about each other's results. Third, that measurements produce single definite outcomes. The inequality was violated by 5 standard deviations. That means at least one of those 3 assumptions is wrong. Either quantum mechanics breaks down at some scale, or different observers cannot consistently compare their results, or measurements do not produce single definite outcomes. And the experiment could not determine which assumption fails. All it could confirm is that the 3 together are incompatible. You have to give up at least one. The lead author stated it plainly. The scientific method relies on facts, established through repeated measurements and agreed upon universally independently of who observed them. Their experiment demonstrated that this reliance may be misplaced. At the quantum level, observer-independent facts may not exist. Now, the friends in this experiment were photons, not conscious beings. Whether this fully instantiates Wigner's original thought experiment is debatable. But that is precisely the point. The experiment works with photons. It does not require consciousness. The paradox arises from physical correlations, not from minds. And what it says about reality is that the thing we call a fact, the idea that something happened and it happened in one definite way, may be a feature of our macroscopic experience rather than a feature of the universe itself. You were told the double slit experiment is strange because observation affects reality. The Wigner's friend experiment says it is stranger than that. It says reality may not have a single version that all observers can agree on. And it says this not because of consciousness, but because of the mathematical structure of quantum mechanics applied to systems that observe each other. So now you have the full picture of what the experiments say. The first layer says observation collapses the wave function. The second layer says consciousness is not the observer that matters. And underneath even the second layer, there is a question that nobody has answered. If reality depends on observation, but observation is not consciousness, then what is observation? What does it actually mean, physically, for something to be observed? The physics community has 6 different answers. They have been arguing about those 6 answers for nearly a century. And the argument is far more vicious, far more personal, and far more consequential than anything the public has been told. The standard answer, the one taught in most universities and repeated in most textbooks, is the Copenhagen interpretation. And the first thing you need to understand about the Copenhagen interpretation is that it is not actually an interpretation. It is a refusal to give one. The Copenhagen interpretation is associated primarily with Niels Bohr and Werner Heisenberg, the architects of quantum mechanics in the 1920s. But Bohr and Heisenberg did not agree with each other about what it meant. Heisenberg introduced the idea that the wave function literally collapses when a measurement occurs, jumping instantaneously from a spread-out superposition to a definite state. Bohr rejected that picture. Bohr's position was subtler and in some ways more radical. He argued that quantum mechanics does not describe what nature is. It describes what we can say about nature. The wave function is not a physical thing that collapses. It is a mathematical tool for calculating the probabilities of experimental outcomes. Asking what the electron is really doing between measurements is not a question that physics can answer. It is not even a meaningful question. Bohr formalized this into his principle of complementarity. Certain descriptions of reality, wave and particle, position and momentum, are mutually exclusive but jointly necessary. You can use one or the other, but never both at once. When Bohr was awarded the Order of the Elephant by the Danish king in 1947, he designed his coat of arms with a yin-yang symbol and the Latin motto, Contraria sunt complementa. Opposites are complementary. He meant it literally. The problem with Copenhagen is that it draws a line between the quantum world and the classical world and refuses to say where the line is or why it exists. Measuring instruments, Bohr insisted, must always be described entirely on classical lines. But measuring instruments are made of atoms. Atoms obey quantum mechanics. Where exactly does quantum stop and classical start? Copenhagen does not say. It tells you to shut up and calculate. It tells you the question is meaningless. And for 80 years, the majority of working physicists have accepted this, not because the answer is satisfying, but because the calculations work. Quantum mechanics predicts experimental outcomes to extraordinary precision. The quantum electrodynamics calculations agree with experiment to 11 decimal places. Why worry about what it means when the math works this well? The answer to why worry is the double slit experiment. Because the double slit experiment puts the question directly in your face and refuses to let you look away. A particle goes through both slits and one slit depending on whether you check. Copenhagen says do not ask what the particle is really doing, but the experiment is asking. The experiment is forcing the question, and shut up and calculate is not an answer. It is an abdication. Bohr himself seemed to understand this, even if he refused to cross the line. He once said, "It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature." That sentence has been quoted approvingly for decades by physicists who think it represents wisdom. But read it again. A discipline that was founded to understand the natural world officially declared that understanding the natural world is not its job. That is not a theory. That is a surrender. And the people who tried to fight that surrender paid for it. The history of quantum foundations is littered with careers damaged, papers ignored, and ideas suppressed, not because they were wrong, but because they tried to answer the question that Copenhagen said was not worth asking. Consider what happened to the idea of hidden variables. In the 1920s, when quantum mechanics was being formulated, several physicists proposed that the apparent randomness of quantum outcomes might be explained by variables we cannot see. Hidden variables, like the exact position and velocity of every molecule in a gas, which we cannot track individually, but which determine the gas's behavior through deterministic mechanics. Maybe quantum randomness is the same kind of thing. Maybe particles have definite properties at all times, and we just cannot measure them with enough precision. Einstein believed something like this until the day he died. In 1935, he published the EPR paper with Boris Podolsky and Nathan Rosen, arguing that quantum mechanics must be incomplete because it predicts correlations between distant particles that seem to require either faster-than-light influences or pre-existing hidden properties. Einstein was sure it was the latter. God does not play dice, he said, though the original German, Der alte Würfelt nicht, translates more accurately as the old one does not play dice, a reference not to a religious deity, but to the impersonal cosmic order that Einstein believed in deeply. The mainstream physics community sided with Bohr. Hidden variables were considered a dead end, and for 20 years that consensus held firm, reinforced by von Neumann's flawed proof and by the enormous practical success of quantum mechanics as a calculational tool. Nobody needed to answer the foundational question. The theory predicted every experimental result. It built lasers and transistors and nuclear reactors. It worked. And if it worked, why worry about what it meant? That was the atmosphere into which David Bohm published his pilot wave papers in 1952. In 1952, a physicist named David Bohm published 2 papers in Physical Review that should have changed the direction of quantum mechanics forever. They proposed a completely deterministic, fully visualizable explanation for every quantum phenomenon, including the double slit experiment, without invoking wave function collapse, without requiring consciousness, without any mysterious boundary between quantum and classical, and without a single prediction that differed from standard quantum mechanics. Every experiment that confirms Copenhagen also confirms Bohm's theory. Every number that quantum mechanics gets right, Bohm's theory gets right. And yet for decades it was ignored, dismissed, and in some cases actively suppressed. Here is what Bohm proposed. The particle is real. It exists. It has a definite position at every moment. It goes through one slit, not both, but there is also a wave, the pilot wave, that passes through both slits and interferes on the other side. The particle surfs the pilot wave. It follows a definite trajectory determined by the wave's interference pattern, guided by a precise mathematical equation. Over many runs, the particle's positions distribute themselves according to the Bohm rule, the probability distribution that standard quantum mechanics predicts. The interference pattern emerges naturally from the trajectories, not from superposition, not from the particle being in two places at once, but from the wave guiding the particle along paths that concentrate in bright bands and avoid dark bands. When a detector is placed at the slits, the pilot wave changes. The detector becomes entangled with the particle, altering the guiding wave in a way that redirects the particle's trajectory. The interference pattern disappears, not because consciousness observed anything, not because a wave function collapsed, because a physical interaction changed the wave, and the wave changed the particle's path. Everything is physical, everything is deterministic, everything makes mechanical sense. And Bohm's life was destroyed for proposing it. David Bohm was born in Wilkes-Barre, Pennsylvania, in 1917. He studied physics at Penn State and then at Berkeley, under Robert Oppenheimer. He was talented, creative, and politically left-leaning in an era when that combination was dangerous. In 1949, the House Un-American Activities Committee subpoenaed Bohm to testify about his colleagues' political affiliations. He invoked the Fifth Amendment. He was arrested for contempt of Congress. Although he was later acquitted, Princeton University, where he had been working as an assistant professor, suspended him immediately. He was barred from setting foot on campus. He was barred from even using the university library. Einstein, who was at the Institute for Advanced Study in Princeton at the time, wanted to hire Bohm. Oppenheimer, who was now director of the institute, blocked it. The man who had led the Bohm project refused to hire one of his own former students because of the political climate. Bohm fled the country. He went to Brazil, then to Israel, then to England, where he spent the rest of his career at Birkbeck College in London. His American passport was confiscated. He did not recover United States citizenship until 1982. The pilot wave theory Bohm proposed in 1952 was not even original to him. Louis de Broglie, the French physicist who first proposed that matter has wave-like properties, had presented essentially the same idea at the Fifth Solvay Conference in 1927. De Broglie's pilot wave theory was attacked at the conference by Wolfgang Pauli, and de Broglie, intimidated by Pauli's reputation, abandoned it. For 25 years, nobody touched it. Then Bohm reinvented it independently, and the physics community went after him too. The reason was a theorem. In 1932, the Hungarian mathematician John von Neumann published a proof in his textbook on quantum mechanics that purported to show that no hidden variable theory, no theory where particles have definite positions at all times, could reproduce the predictions of quantum mechanics. Von Neumann's proof was treated as gospel for decades. It was cited in textbooks, invoked in arguments, used to dismiss any attempt at a deterministic completion of quantum mechanics. If von Neumann proved it is impossible, there is nothing to discuss. But the proof was wrong, and a German mathematician named Greta Hermann identified the flaw in 1935. 3 years after the proof was published, Hermann wrote a paper showing that von Neumann had made a circular assumption. He had assumed that the expectation value of a sum of observables equals the sum of the expectation values even for hidden variable states. That assumption is true for quantum states, but is precisely the thing that needs to be proved for hidden variables not assumed. Hermann pointed this out clearly and precisely. Her paper was published in a respected journal, and nobody paid any attention. For 30 years, her correction was ignored. Von Neumann's proof continued to be cited as the definitive argument against hidden variables, even though it had been refuted. It was not until 1966 that John Stuart Bell, an Irish physicist working at CERN, independently discovered the same flaw. Bell's reaction was not diplomatic. He wrote that von Neumann's proof was not merely false but foolish. Bell went on to derive his own theorem, Bell's inequality, which set genuine testable limits on what hidden variable theories could do. But Bell's theorem does not rule out Bohm's theory. It rules out local hidden variables. Bohm's theory is non-local. The pilot wave connects distant particles instantaneously. Bell knew this. He was a vocal defender of Bohm's theory throughout his career. He said publicly that pilot wave theory was the clearest account of quantum mechanics, and that it is a great mystery to me that it was so generally ignored. Bell himself was treated as something of an outsider for his interest in foundations. The prevailing attitude in physics departments throughout the 50s, 60s, and 70s was that the foundations of quantum mechanics were a solved problem. Copenhagen had answered the questions, or rather, Copenhagen had declared the questions meaningless, which was treated as the same thing. Physicists who asked foundational questions were seen as philosophers, not scientists. Bell's inequality was arguably the most important result in theoretical physics in the second half of the 20th century, and Bell died of a cerebral hemorrhage in 1990 at the age of 62. Just months before his work was recognized with the nomination for the Nobel Prize, he never received it. The prize went instead to the experimentalists who tested his theorem 32 years after his death. Bohm exiled, de Broglie silenced, Hermann ignored, Bell unrecognized. There is a pattern here, and the pattern has nothing to do with the quality of the physics. The pattern is that anyone who tried to give a clear physical, visualizable account of what is actually happening in quantum experiments was marginalized by a community that had collectively decided the question was not worth asking. Copenhagen's refusal to answer became the orthodoxy, and anyone who tried to provide an answer was treated as a crank, regardless of the mathematical rigor of their work. This matters for the double slit experiment because the question at the center of the second layer, what does observation actually mean, is the question these people tried to answer. Bohm answered it. Observation is a physical interaction that changes the pilot wave. Bell clarified what kinds of theories could work. Greater Hermann identified a fatal error in the argument against them, and the mainstream physics community, for decades, preferred the comfort of not answering to the difficulty of accepting their answers. But there is one development that has cut through the interpretive debates, one framework that nearly every physicist accepts as correct, regardless of their preferred interpretation. And it offers the clearest picture we have of what observation means at the physical level. It is called decoherence, and its history is almost as much a story of suppression as Bohm's. In 1970, a German physicist named H. Dieter Zeh published a paper in Foundations of Physics titled On the Interpretation of Measurement in Quantum Theory. It was one of the most prescient papers in the history of quantum foundations, and it was almost completely ignored for a decade. Zeh's insight was this: macroscopic objects are never isolated. They interact with their environment constantly. Air molecules bounce off them. Photons scatter off their surfaces. Thermal radiation flows in and out. Every one of these interactions is a quantum interaction. Every one of them entangles the object with its environment. And when a quantum system becomes entangled with a large number of environmental particles, something happens to its quantum coherence. The delicate phase relationships between different parts of the superposition, the relationships that produce interference, leak out into the environment. They do not disappear from the universe. They become spread across so many environmental degrees of freedom that they are effectively unrecoverable. The system stops looking quantum. It starts looking classical. Not because anything collapsed, because the coherence is now shared with trillions of air molecules and photons that you have no practical ability to track. Ze's paper was sent to a leading physics journal and rejected. He submitted it to Foundations of Physics, a journal considered more philosophical than mainstream. It was published there, and for years, almost nobody cited it. The physics community in 1970 was not interested in the measurement problem. They had Copenhagen, they had Shut Up and Calculate. A paper explaining what measurement actually is, physically, was treated as irrelevant. It took another physicist, Wojciech Zurek at Los Alamos National Laboratory, to develop decoherence into a full framework in the 1980s. Zurek introduced the concepts of pointer states, the preferred states that survive interaction with the environment, and einselection, environment-induced superselection, the process by which the environment picks out certain states, as classical. He later developed quantum Darwinism, the idea that the environment does not just destroy quantum coherence, but actively proliferates copies of classical information. When you look at an object, you are not looking at the object, you are looking at photons that bounced off the object, millions of photons. Each one carries a copy of the same information about the object's state. That redundancy is why multiple observers agree about what they see. The environment has already measured the object and broadcast the result. The implications for the double slit experiment are immediate. When you place a detector at the slits, the detector does not collapse the wave function through some mysterious quantum to classical transition. The detector becomes entangled with the electron. The environment, the air molecules around the detector, the thermal radiation, the electrical currents in the detector's wiring becomes entangled with the detector. The electron's quantum coherence, the information about which slit it went through, diffuses into the environment faster than you can blink. The interference pattern disappears because the which path information now exists in the physical world, distributed across trillions of environmental particles. It does not matter if any conscious being ever reads that information. The information exists. The environment recorded it. And that is enough. The decoherence timescale for macroscopic objects is extraordinarily fast. For a dust grain in sunlight, the quantum coherence between two positions separated by the width of the grain is destroyed in roughly 10 to the negative 20 seconds. That is 100 billion billionth of a second. A single photon bouncing off a dust grain decoheres it. For a bowling ball, the decoherence time is so short that it does not have a meaningful numerical representation in everyday units. The classical world you experience every day is classical not because quantum mechanics stops working at large scales, but because the environment is an unimaginably efficient measuring device, constantly entangling with everything, constantly recording which path information for every particle, constantly broadcasting that information into the world. This is why you never see a chair in two places at once. Not because chairs are too big for quantum mechanics. Quantum mechanics applies to chairs. The Schrödinger equation governs every atom in the chair. But the chair is in contact with roughly 10 to the 27th air molecules, bathed in roughly 10 to the 12 thermal photons per cubic centimeter, exchanging information with its environment through billions of interactions per second. The environment measures the chair's position constantly, redundantly, mercilessly. The chair's quantum coherence, its ability to be in a superposition of positions, is destroyed before it can build up. The chair is in one place because the universe has already asked the question, where is the chair? 10 to the 30 times before you open your eyes. Your observation is redundant. The environment got there first. The environment always gets there first. You live in a universe that is observing itself, every atom measured by every photon, every molecule entangled with its neighbors, every surface radiating information into the void. This is not metaphor. Zurich's quantum Darwinism framework, developed over the 2000s and 2010s, makes this precise. In classical Darwinism, natural selection amplifies certain traits by copying them into future generations. In quantum Darwinism, the environment amplifies certain quantum states by copying information about them into the surrounding world. When a photon bounces off a table and enters your eye, it carries information about the table's position, shape, and color. But your eye is not the only thing that photon could reach. The same information is carried by millions of other photons bouncing off the table in all directions, by air molecules that collide with its surface, by thermal radiation it emits. The environment makes redundant copies of the table's classical state and distributes them throughout the surrounding space. That is why you and I, looking at the same table from different angles, agree on what we see. We are not observing the table directly, we are reading different copies of the same environmental record. This framework was experimentally confirmed in 2019 by Anton and colleagues using nitrogen vacancy centers in diamond, published in Physical Review Letters. They observed the proliferation of quantum information into an environment of nuclear spins and confirmed that observers could independently access consistent information about the system's state. The same framework has been verified on IBM quantum computers by Saini and Behera in 2200 and 2000. Zurich published a comprehensive book on the topic through Cambridge University Press in 2205, Decoherence and Quantum Darwinism, From Quantum Foundations to Classical Reality. The framework is no longer speculative, it is experimentally grounded, and the implication for the double-slit experiment is devastating in its clarity. The interference pattern does not vanish because someone looked. It vanishes because the environment looked. The air molecules in the laboratory looked. The thermal photons looked. Every physical system that became entangled with the electron's path information is an observer, and there are trillions of them, and they are observing constantly, and they do not need permission, and they do not need awareness, and they do not need to be alive. And here is the critical caveat that makes decoherence both the most important and the most frustrating development in quantum foundations. Decoherence explains why we do not see interference at macroscopic scales. It explains why the classical world looks classical. It explains what measurement is, physically, in terms anyone can understand. It is a physical interaction that entangles the system with its environment and spreads quantum coherence into unrecoverable noise. But decoherence does not explain why you see one specific outcome. When the electron goes through the slits and is measured by a detector, decoherence says the interference pattern vanishes because the witch path information has leaked into the environment. Fine, but the electron went through one slit or the other. Which one? Decoherence says both options are still present in the global wave function. The branch where the electron went through slit A and the branch where it went through slit B both still exist. They are just no longer able to interfere with each other. They are, in Zurich's language, decoherent. But they are both there. The universe, according to decoherence alone, has not picked one. You have experienced one, but the math does not say the other was eliminated. This is why decoherence, on its own, does not solve the measurement problem. It explains the disappearance of interference. It does not explain the appearance of definite outcomes. And that is where the interpretations come back in, each offering a different answer to the question decoherence leaves open. Many worlds says both outcomes are real. You experience one because you're in one branch. Another version of you in another branch experienced the other. There is no collapse. There is no selection. There is just branching, and you happen to be on one branch. Sean Carroll, in his 2019 book Something Deeply Hidden, argued that many worlds is the simplest interpretation because it adds nothing to the mathematical formalism. The wave function evolves, that is it. No collapse postulate, no mysterious measurement axiom. Just the Schrödinger equation, all the way down. The price is ontological. You have to accept that the universe is constantly splitting into an incomprehensible number of branches, that every quantum event generates new copies of everything, and that the you reading this sentence is one of an effectively infinite number of yous generated by quantum branching since the beginning of time. David Deutsch at Oxford has gone further. He has argued that many worlds is not an interpretation at all. It is the theory. Calling it an interpretation, he says, is like calling dinosaurs an interpretation of the fossil record. The fossils are there, the bones are real. Calling what they point to an interpretation is a way of avoiding what the evidence actually says. Deutsch insists the branching is real. The other versions of you are real. The entire multiverse is as physical as the chair you are sitting in. And the reason physicists resist this is not that the evidence points elsewhere, it is that the evidence points somewhere they do not want to go. But even many worlds has a problem it has never fully solved. The Bohm rule. In standard quantum mechanics, the probability of an outcome is the square of the amplitude of the wave function for that outcome. Many worlds claims all outcomes happen, so where do probabilities come from? If every branch is real, why do we observe outcomes with frequencies that match the Bohm rule? This is the probability problem, and it has generated a cottage industry of papers attempting to derive the Bohm rule from within many worlds. Deutsch and David Wallace have offered decision-theoretic derivations. Others remain skeptical. The debate is unresolved. And in 2018, two physicists at ETH Zurich proved that the measurement problem may be even worse than anyone realized. Daniela Frauchiger and Renato Renner published a paper in Nature Communications titled "Quantum Theory Cannot Consistently Describe the Use of Itself." Their thought experiment involved 4 agents reasoning about each other's. Quantum measurements. 2 agents are inside laboratories performing measurements. 2 agents are outside, measuring the laboratories as quantum systems. The 4 agents, all applying quantum mechanics correctly, reach contradictory conclusions about each other's results. The paper showed that 3 seemingly reasonable assumptions cannot all be true simultaneously. First, that quantum mechanics applies universally to systems of any size. Second, that different agents using quantum mechanics can reason consistently about each other's results. Third, that measurements produce single, definite outcomes. At least one of these must be wrong. And the paper could not determine which one. Every interpretation of quantum mechanics violates at least one of the 3. Copenhagen violates universality by drawing an arbitrary classical quantum boundary. Many worlds violate single outcomes by accepting all branches as real. Pilot wave theory violates something more subtle in the reasoning chain. Cubism sidesteps by denying that agents can reason about each other's experiences. Renner stated the implication with uncomfortable directness. We have not experimentally established the fact that quantum mechanics applies on larger scales. We do not know whether it extends to objects the size of humans. That sentence, from one of the most respected quantum information theorists alive, should stop you cold. After a century of quantum mechanics, we do not know if the theory applies to us. We do not know if we are quantum systems. We do not know if the rules that govern photons and electrons also govern the neurons in your brain. The theory works perfectly for small systems. Whether it scales to human-sized objects is an open question, and the experiments that could test it, genuine Wigner's friend experiments with conscious observers in superposition, are so far beyond current technology that they might as well be science fiction. Einstein saw all of this coming. He did not live to see the quantum eraser, or the delayed choice experiment, or the Bell test violations. He died in 1955, 30 years before the experiments that would have settled his most important argument with Bohr. But he asked the right question. He asked whether the moon exists when nobody is looking at it. His friend and biographer Abraham Pais recalled that Einstein posed this question during a walk around 1950. Do you really believe that the moon is not there when nobody looks at it? The question was rhetorical. Einstein believed the moon is there regardless. He believed in an objective reality that exists independently of observation. He called this realism, and he believed quantum mechanics was incomplete because it could not describe such a reality. The experiments have vindicated Einstein in one sense and refuted him in another. His realism, the idea that particles have definite properties before measurement, was ruled out by the Bell test violations. Aspects experiments in 1982 and the loophole-free tests by Henson and colleagues in 2015 confirmed that no local hidden variable theory can reproduce the predictions of quantum mechanics. Einstein's specific proposal that quantum mechanics could be completed with local hidden variables was wrong, but his question about the moon was right. The moon is there when nobody looks at it, and the reason it is there has nothing to do with consciousness. It is there because trillions of photons, air molecules, and gravitational interactions are constantly looking at it. The environment is the observer. The moon is decohered into a definite classical state by its interactions with the rest of the universe. It does not need a human mind to make it real. It needs information. And information is being exchanged between the moon and its environment every nanosecond of every day, whether any conscious being is aware of it or not. Pilot wave theory says the outcome was always determined. The particle always had a definite position. The pilot wave guided it to slit A or slit B. Decoherence changed the guiding wave, directing the particle to one definite location. There was never a superposition of outcomes at the fundamental level. There was a wave guiding a particle, and the particle went where the wave sent it. The apparent randomness of quantum mechanics in this picture is not fundamental. It comes from our ignorance of the particle's exact initial position. Cubism, developed by Christopher Fuchs and Rudiger Schack, says the wave function is not a physical thing at all. It is a tool an agent uses to organize their expectations about future experiences. Measurement is an agent's action on the world that results in a specific experience. The outcome is definite because you experienced it. The question of what really happened, apart from your experience, is not a question Cubism answers or considers meaningful. Fuchs once joked, "Dogs do not use wave functions. I did not collapse a wave function until I was 34. Relational quantum mechanics, proposed by Carlo Rovelli in 1996, says quantum states are not properties of systems. They are relations between systems. The electron does not have a polarization. It has a polarization relative to the detector. The detector has a result relative to you. You have an experience relative to the rest of the universe. No observer-independent quantum state exists, just as no observer-independent velocity exists in special relativity. Consciousness is as irrelevant as in every other interpretation. Any physical system can serve as an observer, a rock, a photon, an air molecule. The word observer does not imply a mind. 6 interpretations: Copenhagen, many worlds, pilot wave, Cubism, relational quantum mechanics, and decoherence as a standalone framework. They disagree about almost everything. They disagree about whether the wave function is real. They disagree about whether particles have positions between measurements. They disagree about whether the universe splits. They disagree about whether probability is objective or subjective. They disagree about whether the question, "What is really happening?" is meaningful. But they agree on one thing. Every single one of them says consciousness is not the relevant variable. Not one mainstream interpretation of quantum mechanics assigns a special role to human awareness. Copenhagen says measurement is a physical process involving macroscopic apparatus. Many worlds says all outcomes happen regardless of who observes. Pilot wave theory says particles follow deterministic trajectories guided by waves. Cubism says the wave function is an agent's tool. But agents can be anything. Relational quantum mechanics says observations are physical interactions between systems. Decoherence says the environment is the observer. This consensus is remarkable. Physicists agree on almost nothing when it comes to the foundations of quantum mechanics. They hold conferences where arguments devolve into shouting matches about whether the wave function is real. They write papers accusing each other of philosophical naivety. The interpretive wars have been called the most vicious in all of science, fought with the intensity of theological disputes, because at bottom they are theological disputes. They are arguments about what exists. And yet across all the battle lines, across every school and every camp and every faction, there is unanimous agreement on this one point. The double-slit experiment has nothing to do with consciousness. The quantum eraser has nothing to do with consciousness. The delayed choice experiment has nothing to do with consciousness. The universe does not care about your mind. Every experiment that has tested whether consciousness matters has found it does not. Every interpretation that physicists have proposed to explain quantum mechanics says consciousness is not the variable. The double-slit experiment, the most famous experiment in quantum physics, the one that launched 1,000 books about the power of human observation, has nothing to do with human observation. The universe does not care if you are watching. It cares about something else, and that something else has a name, even if we do not fully understand what it means. Information, that word has appeared in this script dozens of times now, and every time it has been doing real work. When Englert wrote his duality relation, d squared plus v squared less than or equal to 1, d was path distinguishability, the amount of which path information available, and v was fringe visibility, the clarity of the interference pattern. As one goes up, the other goes down. Not because of a mechanical interaction, not because something bumped the particle. Because of information, when the Kim experiment showed that sorting by idler detection reveals hidden interference, the sorting was based on information. Which detector recorded the idler, and the interference was always there, hidden in the correlations, invisible until the information was used to post-select. When Zeilinger's team showed that a causally disconnected random number generator's choice determined whether interference appeared, the choice was a choice about information, whether which path information would be preserved or erased. When decoherence explains the classical world, it explains it in terms of information, which path information leaking into the environment, being copied and redundantly stored across trillions of environmental particles. Every road leads to the same place. The variable is information, not energy, not force, not consciousness. Information. And now we are one section away from confronting what that actually means. Because the question that hangs over everything, the question that physics has been circling for 100 years without landing on, is this. If information is what determines the behavior of reality, then what is information? Is it a thing? Is it made of something? Does it exist independently of the physical systems that carry it? Or is it the other way round? Do the physical systems exist because of the information? There is a man who spent the last 30 years of his life on that question. He did not answer it, but he came closer than anyone else, and his framework, ignored during his lifetime by the popular science machine that preferred the sexier consciousness narrative, may turn out to be the deepest idea in the history of physics. John Archibald Wheeler divided his intellectual life into 3 periods. He described them with characteristic bluntness. Period 1, everything is particles. Period 2, everything is fields. Period 3, everything is information. The first period covered his early career, working with Bohr on fission, working on the Bohm, working on nuclear and particle physics. The world was made of stuff: protons, neutrons, electrons, photons, matter and radiation. The job of physics was to figure out the rules governing the stuff. The second period began in the 1950s and 60s, when Wheeler turned to general relativity and the geometry of space-time. Gravity was not a force. It was the curvature of a field. Space-time itself was a physical thing, bendable and deformable. Wheeler coined the term black hole during a talk in 1967 because the previous name, gravitationally completely collapsed object, was, in his words, not a name to inspire the imagination. He coined wormhole. He explored the idea that all of physics might be geometry, that particles themselves might be features of the geometry of space-time, excitations in the fabric of the field. Everything is fields. But the third period, the one Wheeler arrived at in the 1970s and spent the rest of his life developing, was the most radical of all. He presented it formally at a Santa Fe Institute conference in the spring of 1989 and published it under the title Information Physics, Quantum. The search for links in the proceedings of the Third International Symposium on the Foundations of Quantum Mechanics in Tokyo, the core idea was 3 words: it from bit. Otherwise put, every it, every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely, even if in some contexts indirectly, from the apparatus-elicited answers to yes or no questions, binary choices, bits. Read that sentence carefully. Wheeler is not saying that information describes reality. He is not saying that information is a useful way of modeling physics. He is saying that reality is made of information, that the physical world, the particles and fields and space-time itself, derives its existence from bits. Information is not a representation of the world. Information is the world. The bit comes first. The it comes from the bit. This was not a casual metaphor from a declining mind. Wheeler was meticulous about it. He compiled a list of 20 questions about the nature of reality that he believed physics needed to answer. And the first and most important was, how come the quantum? His proposed answer was that the quantum exists because reality is fundamentally informational, and information is inherently discrete. A bit is 0 or 1. It is not a continuum. The quantization of physics, the fact that energy comes in packets, that angular momentum comes in multiples of Planck's constant, that electrical charge comes in units, might be a consequence of the fact that at the bottom of everything are bits, discrete choices, yes or no, not a smooth reality that we approximate with bits, but a bitwise reality that we perceive as smooth. Wheeler developed this over decades. In his 1983 essay, Law Without Law, he argued that the laws of physics themselves might emerge from the accumulation of quantum measurements. Law without law. Rules arising not from some pre-existing blueprint, but from the pattern of yes or no answers that the universe gives to the questions asked of it. The laws of physics, in this picture, are like the rules of grammar that emerge from a language. Nobody wrote the rules first and then created the language. The language came first, and the rules are descriptions of its patterns. Wheeler illustrated this with a variant of the parlor game, 20 questions. In the standard game, the respondent thinks of an object, and the questioner asks up to 20 yes or no questions to identify it. But Wheeler described a version he called negative 20 questions. In this version, there is no object chosen in advance. The respondent answers each question freely, with only one constraint. Every answer must be consistent with all previous answers. The object is not revealed by the questions. It is created by them. It comes into being through the accumulation of yes or no answers, each answer constraining the space of possibilities until a definite object emerges. Wheeler liked to tell the story of actually playing this game at a dinner party. He left the room, and the other guests were supposed to choose an object. When he returned and began asking questions, the answers came slowly. Each respondent took longer than usual. The answers seemed to meander, but they stayed consistent. After many questions, Wheeler finally guessed cloud. The room erupted in laughter. They told him the secret. Nobody had chosen an object. Each person had simply answered consistently with the previous answers. The cloud had not been there before Wheeler asked. It was summoned into existence by the questions. That, Wheeler argued, is what measurement does. A quantum measurement is not uncovering a pre-existing fact about a particle. It is asking a yes or no question, and the answer brings a fact into existence. The photon in the double-slit experiment does not have a definite path before the measurement asks which slit it went through. The measurement creates the path. The electron does not have a definite spin before the detector asks up or down. The detector creates the spin. The physical world, at its most fundamental level, is not a collection of objects with pre-existing properties. It is a web of questions and answers, each answer constraining the next, each bit of information defining a piece of reality that did not exist before the question was asked. This is not philosophy. This is the most literal reading of what the experiments show. The delayed choice experiment demonstrates that a photon does not have a definite history until a measurement defines one. The quantum eraser demonstrates that the history can be undefined, defined, and undefined again depending on the availability of information. The entanglement swapping experiments demonstrate that correlations between particles can be created retroactively by a measurement performed after the particles were detected. In every case, the measurement creates the fact, the bit creates the it, and this is why the consciousness debate was always a distraction. Consciousness is not asking the question. A machine can ask the question. A quantum random number generator can ask the question. A photon bouncing off a dust grain can ask the question. Any physical interaction that irreversibly registers a binary answer that records one bit of information about a quantum system is a measurement. It creates a fact. It brings an it from a bit. The universe does not need a mind to ask questions. It asks them of itself, constantly through every physical interaction, trillions of times per second, in every cubic centimeter of space, building reality from bits, one answer at a time. Wheeler's closing vision, written when he was nearly 80, was this: someday we can believe, we will grasp the central idea of it all as so simple, so beautiful, so compelling, that we will all say to each other, "Oh, how could it have been so blind so long?" He died on April 13th, 2008, at 96, of pneumonia, at his home in Hightstown, New Jersey. His wife Jeanette had died 6 months earlier, in October 2007, after 72 years of marriage. Wheeler had maintained an office at Princeton's Jadwin Hall until 2006, often working 12-hour days well into his 90s. At nearly 80, he still refused elevators, charged down stairwells hooking his arm around banisters for centrifugal force, and raced ahead of visitors to hold doors open. A journalist once wrote that the metaphor was so obvious he wondered whether Wheeler intended it. The man had spent his entire life racing ahead and throwing open doors. Doors that led to black holes, to wormholes, to nuclear fission, to the participatory universe to it from bit. Every door he opened revealed another door behind it. He never found the last one. He never expected to. He once said his biggest ambition was to learn how come existence. He did not achieve it. Nobody has. But nobody got closer by running at the question harder. He did not live to see his students' vindication. Anton Zeilinger, who studied the foundations that Wheeler had helped lay, won the 2022 Nobel Prize in Physics alongside Alain Aspect and John Clauser for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Zeilinger had spent decades pushing the experimental boundaries of Wheeler's ideas. He demonstrated quantum teleportation over 144 kilometers between the Canary Islands. He contributed to the design of China's Messius quantum satellite. In 2017, his team ran the cosmic Bell test, using photons from quasars emitted hundreds of light years ago to set measurement choices, closing the freedom of choice loophole in Bell tests by ensuring that the measurement settings were determined by events that occurred before the Milky Way formed. That experiment deserves a moment. Think about what it means. The measurement settings in a Bell test need to be random, genuinely unpredictable, to close the loophole that perhaps some hidden variable correlated the settings with the particles in advance. Most experiments use random number generators, but even a random number generator is a physical device, and its output is determined by its initial state, which is part of the same universe as the particles being measured. In principle, some cosmic conspiracy could correlate them, so Zeilinger's team used the color of photons arriving from distant quasars as the random input. The photons left those quasars 600 years ago in one case, and over 7.8 billion years ago in another. For any hidden variable to have correlated the measurement settings with the test particles, the conspiracy would have had to be set in motion before the light left those quasars, before humanity existed. Before Earth existed in the case of the more distant quasar, the experiment found Bell inequality violations with a p-value less than 10 to the negative 9, effectively ruling out any freedom of choice conspiracy originating within the last 7.8 billion years. The universe is not cheating, the correlations are real, and they work the same way regardless of whether the measurement choices are made by humans, machines, or ancient starlight. Zeilinger, more than any other living physicist, has championed the information theoretic view that Wheeler pioneered. In his 1999 paper, A Foundational Principle for Quantum Mechanics, published in Foundations of Physics, Zeilinger proposed that the most basic principle underlying quantum mechanics is this: an elementary system carries one bit of information, one particle, one bit. That is all it can hold. If you measure its spin, you use up the bit. It gives you a definite answer to up or down. But now it has nothing left. Its position, its momentum, everything else is maximally uncertain. Not because you disturbed it, because it only had one bit to give. The randomness of quantum mechanics, in this picture, is not a failure of knowledge. It is a feature of a universe where information is finite. This is the deepest explanation anyone has offered for why the double-slit experiment works the way it does. The electron can show you interference, or it can show you which slit it went through. It cannot show you both, not because of a limitation in your technology, not because of the uncertainty principle applied to your instruments, because the electron does not have enough information to answer both questions at once. One bit, one answer. You choose the question and the answer defines the reality. Choose to ask which slit, and you get a particle. Choose to ask what pattern, and you get a wave. The electron is not being coy. It is not hiding something. It genuinely does not have a fact about its path and its interference pattern simultaneously. The fact does not exist until you ask the question that creates it. Zeilinger's statements on the implications are striking. He has said, "The distinction between reality and our knowledge of reality, between reality and information, cannot be made. And we have tried for centuries to look deeper and deeper into finding causes and explanations. And suddenly, when we go to the very depths, to the behavior of individual particles of individual quanta, we find that this search for a cause comes to an end. There is no cause." And in his 22 Nobel lecture, He said, maybe we need a unification between the concepts of reality and information. That sentence, from a Nobel laureate accepting the highest honor in physics, should have been the lead story on every science news outlet on the planet. It was not. The man receiving the prize for the most fundamental experiments in quantum mechanics is telling you that reality and information might be the same thing, that the distinction between the world and the data about the world might not exist, that the it and the bit are not two things. They are one thing. And if they are one thing, then everything you think you know about what the universe is made of, matter, energy, particles, fields, is not the bottom layer. The bottom layer is bits, answers to yes or no questions, information with no substrate, data with no hard drive, a record that exists without anyone to read it and without anything to write it on. And that one thing is what the double slit experiment has been pointing to since 1803. What Thomas Young saw with his sunbeam. What Johnson saw in his basement in Tübingen. What Tonemura saw in his 70,000 dots. What Kim saw in his coincidence counts. What Zeilinger saw in his entangled photons crossing the Atlantic. The experiment never changed. Only our ability to hear what it was saying. When Thomas Young split a sunbeam with a thin card and saw interference fringes, he was not just discovering that light is a wave. He was discovering that the behavior of light depends on the structure of the information available about it. Two beams overlapping with no way to distinguish which photon came from which side of the card produce interference. Block one beam, making the information available, and the interference vanishes. The experiment always was about information. Young did not have the language to say so. Bohr danced around it with complementarity. Heisenberg obscured it with the uncertainty principle. Copenhagen hid the ball under a cup and declared the game over. But the ball was always there. Information. And the experimental tradition that followed Young has been tightening the screws on this insight for over 2 centuries. Each experiment more precise than the last. Each one closing another escape route. Each one pointing more definitively at the same conclusion. Johnson's electrons, 300 nanometers wide slits in copper foil, 1961. A man working alone through late nights, fabricating an apparatus no one thought possible, producing stripes that proved the most famous thought experiment in physics was physically real. His work ignored for 13 years. Feynman telling students the experiment had never been done. 4 years after it had been done. Tonemura's single electrons, one at a time, 70,000 dots forming a wave pattern. 1989. Each electron indivisible, each electron landing as a point. The accumulation of points producing a pattern that is only possible if each electron explored both paths. Information about both slits encoded in the trajectory of a single particle. Scully and Drule's theoretical proof, 1982, that interference vanishes not because of mechanical disturbance, but because of entanglement. Information, not momentum, as the variable. The first crack in the standard explanation. The first glimpse of the second layer. Kim's quantum eraser, interference hidden in the correlations, visible only when sorted by information, 2000. The signal photon arriving 8 nanoseconds before the idler. The total pattern at D0, always a blob. The interference always there, always hidden, always requiring the idler information to reveal. The most misunderstood experiment in physics, the one that launched 1,000 wrong videos and 1,000,000 wrong conclusions about consciousness reaching backward through time. Jacques' single photons, 48 meters of interferometer, a quantum random number generator choosing 2007. The first definitive single photon delayed choice experiment, 94% interference visibility, error probability below 1%, a machine choosing Wheeler's 1978 thought experiment confirmed exactly. Mars entanglement swapping in Vienna, 2012. A quantum random number generator deciding 520 nanoseconds after Alice and Bob had already measured and recorded their results. The correlations in the already recorded data changing retroactively based on a machine's choice. No human in the loop. Mars causally disconnected quantum erasure, 2013, 144 kilometers between La Palma and Tenerife, space-like separation. Einstein locality conditions, a random number generator making the choice with no possible causal connection to the experiment. The results matching quantum mechanics exactly. The Big Bell test, 2018, 100,000 humans versus machines, 97 million random bits from a video game, 13 experiments, 12 laboratories, 5 continents, human choices and machine choices producing identical Bell inequality violations, the most direct test ever performed of whether consciousness matters. It does not. The universe does not distinguish between a deliberate human decision and a random electronic fluctuation, between a philosopher choosing and static choosing, between intention and accident. The variable is not who asks the question or how. The variable is that a question was asked at all. Proietes Wigner's Friend, 2019. 6 photons at Heriot-Watt University. Observer-dependent facts. Bell inequality violated by 5 standard deviations. The assumptions of universal quantum mechanics, consistent reasoning between observers, and single outcomes shown to be jointly incompatible. The idea of a single objective reality, agreed on by all observers, challenged by experimental data. 220 years of experiments, every single one of them saying the same thing in different ways, with increasing precision and decreasing ambiguity. The behavior of reality is determined not by what you know, not by what you observe, not by whether you are conscious or alive or capable of experience, but by the structure of information itself, by what is knowable in principle, by whether a record exists, anywhere, in any form, accessible or not, read or unread, processed or abandoned. The universe does not watch itself through your eyes. It writes itself through the existence of bits. And that is the second layer of the double slit experiment. Not the spooky consciousness story, not the mystical the universe responds to human awareness narrative, not the New Age quantum manifesting nonsense, the actual, published, experimentally verified, peer-reviewed second layer, the one that has been sitting in the physics journal since 1982, confirmed and reconfirmed for over 40 years, and systematically underrepresented in every popular account of quantum mechanics you have ever encountered. The delayed choice quantum eraser did not just confirm that observation collapses the wave function, it confirmed that the decision to observe or not observe can be made after the particle has already landed on the detector. The pattern changes retroactively. The particle's past is rewritten by a choice made in its future. But the second layer is worse. In 2012, researchers showed that you do not even need a conscious observer. The choice can be made by a random number generator, a machine with no awareness, no intention, no understanding, flips a switch, and the past reorganizes itself to be consistent with that flip. Reality does not care who is watching. It does not care if anyone is watching. It restructures itself around the mere mechanical possibility of information being available. The universe is not responding to consciousness. It is responding to something else entirely. And we have no idea what that something is.